So today we're discussing thermodynamic processes and their associated gas laws. And what we are going to do is basically the foundation part to this. Then the second part is where we'll now do the other part that will remain, which is a notch higher than this one, trying to prepare us for the cycles that we'll handle much later. So you will notice that gas laws, some gas laws have their associated processes, the ones that we're going to consider. So look at the first one. The very first one we're considering, an isothermal process. The word isothermal, when you split it, it has iso and then thermal put together. Iso, basically, we've used it in the past to refer to something that remains the same. Thermal referring to temperature. So an isothermal process refers to that kind of process to carry out on a gas at a constant temperature. As long as the temperature remains constant throughout that process, then that process is an isothermal process. And this applies Bohr's law. According to Bohr's law, when you're given a particular quantity of gas, the amount, as long as the temperature is the same, then the absolute pressure is going to be inversely proportional to the volume of that gas. Mathematically, we write it like this. P1 V1 is equal to P2 V2, or PV equals constant. That is Bohr's law. Or basically, we're talking about applying an isothermal process. The next one is an isobaric process. Even by looking at the word itself, isobar, you can see the first word there. If we were to split, we have iso followed by bar. Bar is a unit sometimes used for determining or measuring pressure. And so here, when we put together isobar, it's referring to an isobaric process, which is referring to that process which is carried out at a constant pressure on that gas that you're dealing with or that has been given. The gas law that you might have dealt with, the gas law that is associated with this is Charles' law. So according to Charles' law, as long as the pressure remains the same, then the volume is directly proportional to the absolute temperature. Mathematically, we write it like that. V1 over T1 equals V2 over T2. But the shortcut, the shortened version is simply V over T equals constant. So once again, what is an isobaric process? An isobaric process is a kind of process which is carried out on a gas at a constant pressure, or a kind of process where the pressure remains constant throughout. A kind of process where the pressure remains constant throughout. That is an isobaric process. There is also what is known as an isocoric process. Isocoric process this time refers to the volume being kept constant. As long as the volume of a given mass of gas remains constant throughout, then what you're applying is an isocoric process, meaning you could be handling a process being conducted in a fixed container whose boundaries are not movable, and that quantity is also not moving, it remains the same. It's not changing. So this one, we apply the pressure law. The pressure law is the one associated with this process, where as long as the volume remains constant, then your absolute pressure is proportional to your absolute temperature. We're using the word absolute because the pressure must be converted. If you've been given the gauge pressure, you must convert it to absolute pressure for you to use it in the calculations. The temperature, if you've been given the temperature in Celsius, which is traditionally the case, whether it's in Celsius or perhaps in Fahrenheit, convert it to the absolute scale, which is the Kelvin. And to do that, you just had 273. We'll get back to that sooner. So the actual equation is P1 over T1 is equal to P2 over T2. Meaning PT, P over T, please, this is not supposed to be V. It's supposed to be P over T equals constant. I'm not highlighting. Let me pick a pen. Let me just pick a pen. Yeah. This is our T. P. Oh, all right. It's just okay. This is not supposed to be V, but P over T equals constant. I think the handout I'm going to share, that will be taken care of. Then we also have an ideal gas law. In an ideal gas law, we are combining all those processes we've referred to, where we're saying as long as you've been, for a given mass of gas, the absolute pressure is going to be directly proportional to the absolute temperature and also inversely proportional to the volume, giving us this master here. In other words, P1 V1 over T1 is equal to P2 V2 over T2. The shortened version is PV over T equals constant. Let me go through that again. We're saying that this whole thing here remains constant. For a given mass of gas, the absolute pressure is going to be inversely proportional to the volume, but directly proportional to the absolute temperature. That's the ideal gas law. So in writing it mathematically, this is it. PV over T equals constant. But because we've said constant, we can also express this in terms of the constants, which are mass and some other given parameter. So in this case, it's like this. We write it as PV equals Mr. T, like PV over T equals MR, the other constant we refer to. This being the characteristic gas constant, and this being the mass of your gas. The mass of a gas is supposed to be given in kgs as per standard. So PV equals MRT. So here we're simply emphasizing what those are standing for. The last process we're talking about is known as an adiabatic process. This is the kind of process where this time around is the heat energy that remains constant throughout that process or when that process is being carried out. So it could be that maybe you are using some jacket or some lagging to preserve that heat, to make sure that the heat, quantity of heat, the amount of heat does not change. So heat transfer in this case is 0. Mathematically, we're saying P1 V1 power gamma equals P2 V2 power gamma. The gamma, this power here, is known as an adiabatic index. So the shortened version of this expression is PV raised to power gamma is equal to constant. PV raised to power gamma equals constant. Deliberately, for this one, we've also added the expression for work done. For work done, it's P1 V1 minus P2 V2 over gamma minus 1. That's one way. But because we've already said PV equals MRT, you can substitute where there's PV, you put this. So it will look like this. P MRT1 minus MRT2, because this P1 V1 is going to be equal to MRT1. And hence the same for this one. P2V2 is going to be equal to MRT2. So divided by gamma minus 1. Now you can already see that MR is constant. Why not factorize? So we factorize, MR is common. Inside the brackets, we have T1 minus T2 divided by gamma minus 1. So that's meaning that if you're looking for work done, you can either use this expression or the expression we have up here. Okay, pick something for highlighting. Oh, sorry. Yeah, just a pointer. Great. Now, having said this, let's try to look at an example that will apply what we've just discussed. Here's our first example. In this example, we've been given a gas occupying 0.001513 cubic meters at a gauge pressure of 90 kilopascals, temperature 30 degrees Celsius, volume 0.008 cubic meters after the compression, and also the temperature rising to 110 degrees Celsius. So given this, we can now put together the data. First is the volume. We've been given that the initial volume is 0.00516 cubic meters. The pressure, the gauge pressure was 90 kilopascals. Converting the kilopascals to pascals, we multiply by 1,000, so we have 90,000 here. But then we need to convert it to the absolute value. So we add the atmospheric pressure. The atmospheric pressure, the average value agreed for the sake of calculations is 100,000, but the actual, the specific value is 101,300, 101,300 pascals. But otherwise, for calculations, this is allowed. This is what we will be using. So 90,000 plus 100,000. Our answer is 190,000. Here, we're just trying to explain where this value is coming from. So this is now the absolute pressure, the one we talked about. Let me emphasize. When you're putting down your data, as long as there's gauge pressure, do not proceed. First, as long as you've been given this gauge pressure, do not proceed to the calculation. First, make sure you convert that gauge pressure to absolute pressure. Then you can go ahead and use it in the calculation. Temperature number 1 should also be converted from the Celsius to the Kelvin, or from the value provided, to make sure it's in the absolute scale. How do you do that? You add 273. You add 273. This is because the 273, this constant number, the Kelvin scale starts at negative 273.15 or thereabout. So if you are lagging by 273 units, you have to add them the moment you're dealing with the absolute value. So converting, just add 273 to the Celsius value, then you've converted. So what we have here is 303 Kelvin. Volume number 2 we're given was 0.0008. So there we have it. Then temperature number 2, 110 must also be converted the same way we've done here. Temperature number 2, we have to convert it also. And it's like T2, 110, we're still adding the same value, 273. What you get is 383. What is the question asking for? Is pressure number 2. Now, the clue that you have is that looking at the equations that we had, what we discussed, the first thing you can notice is that we have 1, 2, 3, 4, 5 parameters. We're looking for parameter number 6. The only one that is able to handle this from what we discussed is the ideal gas law, which has 6 of them. So since we have 5, we're just missing the last one. And whenever you've been provided the data, it will always lead you to one of the gas laws. So in this case, it has led us to the ideal gas law. So here we rewrite the ideal gas law. P1 V1 over T1 is equal to P2 V2 over T2. Now making P2 the subject is P1 V1 multiplied by T2 divided by P1 divided by T1 over V2 because it has now migrated. So this one, whichever way you do it, it's just the algebra maneuvering. You can decide to even just substitute from there and proceed with the working. The value will still be the same. So here, I'm now substituting. My pressure one, my absolute pressure one was 190,000. Volume one was 0.00516. Temperature number two, found it to be 583. Temperature one was 303. And volume two was 0.0008. What is our final pressure? It's 1.55 times 10 power 6. 1.55 times 10 raised to power 6, which in this case, I decided to write it as megapascals just to shorten it. So what you will see on your calculator is supposed to be 1.55 by 10 raised to power 6, which is basically a mega. Or you see the number split there with everything appearing in a way with all the zeros coming after this. But this is our final answer. Now, what kind of answer have we found? This is our final absolute pressure. This is our final absolute pressure. If we need to find the gauge pressure, we will have to subtract the atmospheric pressure and we get back what we want. But for now, the question simply asked us to find the final pressure. So we'll leave it like that in absolute form. If you want, you can even indicate absolute. Example 2. Here we have a compression ignition engine or a CI engine, which is having air at 4.5 bar. Then the compression is taking place according to this 10 to 1. So if it's obeying this law, we're required to calculate the final pressure and the final pressure, assuming this time we're dealing with this law. Okay, now that being the case, we can start writing down the data. First, you interpret the volume. It means V1 over V2 is 10 over 1. That's what you have there. But this is where I always tell people you don't need to stress. This is a volume ratio. And this is being a volume ratio means what I have here is the first volume. What I have second here is the second volume. Meaning if I was to be given the actual volume of this gas, this is how it's going to behave. 10 units reduced to 1. So for now, for the sake of this calculation, for me to get the pressure, I'll put V1, 10 units, V2, 1 unit. So hence, just put it like that. V1, 10, V2, 1. Or you start by saying V1 over V2 is 10 over 1. So that you just cross multiply and proceed. It's basically the same thing. Then we don't forget, we've already been given the pressure here. This pressure that we've been provided with is 4.5 bar. Now here the secret is this: as long as the pressure that you've been given, the language is simply saying pressure, then that is basically your absolute pressure. That becomes your absolute pressure. You don't need to stress. So here we have it. P1, 4.5 by 10 power 5. We don't need to convert it because this is not gauge pressure, but it's absolute. Let's find the final pressure then. Now here, first of all, we have P1, V1 is equal to P2, V2. If I make P2 the subject of the formula, I'll have P1, V1 over V2. I divide through by V2. Then this is what I have. Having done that, I can now substitute. My P1 was 4.5 by 10 power 5. Volume 1 was 10. Volume 2, 1. So then, when I multiply this by 10 and divide by 1, that's the answer, 4.5 by 10 raised to power 6. Let me go through that again. I have P1 V1 equals P2 V2. So just make P2 the subject of the formula. All I do is divide both sides by V2 so that I can remain with P2 on one side. So then P1 V1 over V2. Then I have this, which is P2, which I'm looking for. For now, I can just substitute. P1 is 4.5 by 10 power 5. Then V1 is 10 divided by 1. What is my P2? Pressure 2 is 4.5 by 10 power 6 pascals or newtons per square meter. The second part of the question gave us the law being PV power 1.4 equals constant. So, which means P1 V1 power 1.4 equals P2 V2 power 1.4. Let me come back again. Part A was saying, according to the law, PV equals constant, meaning we use the other expanded version where we plant the various positions. P1 V1 equals P2 V2. The same thing here. In the question, it was written PV power 1.4 equals constant. So we expand it. P1 V1 power 1.4 equals P2 V2 power 1.4. Then we can, this time around, I decided to just do the substitution. In place of P1, I still have 4.5 by 10 power 5. V1 is 10. This time it's being raised to power 1.4. Then P2 multiplied by 1, this 1 is being raised to power 1.4. 1 is a stubborn number. Whatever value you can give it, you always come back to 1, whether you give it 0, 1 million, name it. It will always be 1. So this doesn't change anything. So when you multiply here, what you're going to get is P2 equals 11,303,488. So as you can see, this is our final answer. We also have an exercise. I want you to go through this. As usual, as per tradition, I've also attached the answers so you can take your time, see if the answers you're getting are correct, and you can always let me know. Once again, feel free to type your questions or any clarifications in the comment section. And remember, I know you are very busy. When you subscribe, it will be easier for you to notice the moment I post, you're able to see that this video has been posted. For now, we can end here. Next lesson, we'll dig deeper into the application of the thermodynamic processes.